Welcome to the world of digital electronics, where logic meets innovation to power modern technology. Welcome to the topic of logic gates. A logic gate is a basic digital circuit element that performs a Boolean operation on one or more inputs and produces a single output. In digital electronics, oh yes, we work with only two signal levels, 0 and 1. These represent low and high logic states. Using these binary values, logic gates implement Boolean algebra, which is the foundation for how digital hardware makes decisions and processes information. We begin with the fundamental gates, NOT, AND, and OR. The NOT gate inverts the input, while the AND gate checks whether all conditions are true, and the OR gate verifies whether at least one condition is true. Next up, we delve into the universal gates, NAND and NOR. They are termed universal because one can construct any digital logic function using solely NAND gates or exclusively NOR gates. By the conclusion of this lesson, you ought to be capable of identifying gate symbols, composing the correct Boolean expressions, and validating their behavior using truth tables. And finally, we will also look at waveforms to understand how each gate behaves over time when inputs change. Now, let's understand what exactly is a waveform. A waveform is, simply put, a graph that shows how a signal changes over time. In digital electronics, waveforms are extremely important. Why? Because they help us visualize logic levels, timing, and the relationship between multiple signals in a circuit. A waveform has two axes. The x-axis represents time, and the y-axis represents the signal level, either as a voltage or directly as a logic state. In digital systems, we typically see two flat levels, logic 0, also called low, and logic 1, also known as high. Whenever the signal changes from low to high, we call it a rising edge. And when it changes from high to low, that is referred to as a falling edge. These edges are absolutely critical. Why? Because most digital circuits, like flip-flops, react to edges rather than to steady levels. A pulse occurs when the signal stays high or low for a brief moment. The duration for which it remains high is referred to as the pulse width, also known as T high. The time period, represented by T, is the time taken for one complete repeating cycle of the waveform. From the period, we define frequency, which tells us how often the waveform repeats. Frequency equals 1 divided by period, or F equals 1 over T. Finally, duty cycle tells us what percentage of the period the signal stays high. It is calculated as duty cycle equals T high over T. In conclusion, waveforms, they help us grasp not only the concepts of 0 and 1, but also when signals change. And they illuminate how timing behaves in real digital circuits. Now let's begin with the very first fundamental logic gate, the NOT gate, also known as an inverter. A NOT gate, as you might expect, outputs the complement of its input. That means, without a doubt, the output is, in every case, the exact opposite of whatever you apply at the input. So, if the input is 1, then the output becomes 0. And if the input is 0, then the output becomes 1. The Boolean expression for a NOT gate is written as y equals a bar or y equals a prime. On this slide, you can see it written as y equals a prime. Next, let's confirm the behavior using the truth table. When a is 0, the output Y is 1. When A is 1, the output Y is 0. On the right side, the symbol depicts a triangle, complete with a small bubble at the output. That bubble signifies inversion. This is precisely why the gate flips the input value. To summarize, the NOT gate is a one-input gate that simply produces the opposite logic level at the output. This inverter is utilized everywhere in digital circuits, especially when we require active low signals or when we wish to complement data. A NOT gate. Yes, it's commonly used to invert control signals. Many systems utilize active high signals, whereas others prefer active low signals. Thus, an inverter helps us convert between them. For example, if a block expects an active low reset, but, oh wait, you have an active high reset available, a NOT gate can certainly generate the required polarity. A second common use is bit complementing in data paths. Whenever we need the inverse of a signal, or a data bit, such as forming complements for arithmetic or logic operations, an inverter is the simplest solution. Thirdly, NOT gates are used for reset and enable polarity conversions. In many designs, enables and resets appear in both forms, depending on the block and library cells. Thus, inverters provide clean compatibility. Now, observe the waveform example at the bottom. The top trace is the input A, and the bottom trace is the output Y, which is Y equals NOT A. As A changes over time, like 0 to 1, then back to 0, you can see the output always does the opposite. When A goes high, Y goes low. When A goes low, Y goes high. So, the key takeaway is simple. The NOT gate does not create new logic conditions, it just flips the logic level. And that makes it extremely useful in control and timing networks. A buffer is a logic gate whose output is exactly the same as its input. In other words, it does not change the logic value. If the input is 0, the output remains 0. If the input is 1, the output remains 1. That's why the Boolean relationship is simply Y equals A. So, the question is, if a buffer does not change logic, why do we use it? The most common practical reason is drive strength and fan-out improvement. In real hardware, a signal source cannot drive unlimited loads. Every gate input connected to a signal adds capacitance, and long interconnect wires add even more load. If one signal must drive many gate inputs, the edges can become slow, and the signal may fail timing. A buffer helps by providing higher drive current so one input signal can reliably drive multiple outputs. This improves what we call fan-out, which is the number of standard gate inputs an output can drive without degrading signal quality. On the right, you can see the buffer symbol. It looks like a triangle, similar to NOT but without the small inversion bubble. The truth table at the bottom confirms the behavior. 0 stays 0, and 1 stays 1. So, remember, a buffer is not used to change logic. It is used to make the signal stronger, cleaner, and more reliable for the rest of the circuit. Let's move to the AND gate, one of the most important ASIC logic gates. An AND gate produces an output of 1, or high, only when all of its inputs are 1. If even one input is 0, the output becomes 0, or low. So you can think of AND as a gate that checks whether all required conditions are satisfied. For a two-input AND gate, the Boolean expression is written as Y equals A dot B, or Y equals A, B. For more inputs, the expression extends the same way, Y equals A, B, C, meaning every input must be high for the output to be high. Now look at the truth table. For two inputs, when A and B are 0 and 0, the output is 0. When they are 0 and 1, the output is still 0. When they are 1 and 0, the output is again 0. Only when A is 1 and B is 1, the output becomes 1. On the right side, you can see the standard AND gate symbol. This symbol is used in circuit diagrams to represent the same logic behavior. In real digital design, AND gates are heavily used for enable logic, condition checks, and control decisions. For example, a circuit may turn on only when power OK and enable are both true. So, the key takeaway, AND gate output is high only in the all ones condition. Now, let's explore the typical applications of the AND gate. What about its behavior in a waveform? The AND gate is widely used in enable logic. For example, we may allow a clock or data path to operate only when an enable signal is high. This includes applications like clock enable, reset gating, and data valid generation. Another key use is masking. Masking means we can allow or block a signal using an enable input. If the enable is 0, the AND gate forces the output to 0, so the signal is effectively blocked. AND gates are without a doubt essential in address decoding. Here, multiple conditions must indeed match at the same time, such as selecting a particular memory region or register based on address bits. Finally, AND is used in control logic, especially in state machines, where a transition is permitted only when several conditions are true. This is often referred to as a permission or qualification check. Now, observe the waveform example at the bottom. We have inputs A and B changing over time, and the output Y equals AB. Notice that the output goes high only during the time intervals when A is 1 and B is 1 at the same time. In every other interval, when either A or B is 0, the output stays low. So, the waveform clearly reinforces the rule. The AND output becomes high only when all inputs are high simultaneously. This is exactly why AND gates are so useful for enabling and qualifying operations in digital circuits. Next, let's understand the OR gate, another fundamental logic gate used in digital circuits. An OR gate produces an output of 1 or high when any one or more of its inputs is 1. It produces an output of 0 or low only when all inputs are 0. So, you can think of OR as a gate that checks whether at least one condition is true. For a two-input OR gate, the Boolean expression is written as y equals a plus b, or y equals a plus b. For an OR gate with multiple inputs, the expression extends in a similar manner, y equals a plus b plus c, ... This means that the output is high if any single input is high. Now let's verify this with a truth table. When A and B are both 0, yes, 0 and 0, the output is 0. When the inputs are 0 and 1, guess what? The output becomes 1. When the inputs are 1 and 0, surprise, the output is also 1. And finally, when both inputs are 1, absolutely, the output remains 1. On the right side, you can see the standard OR gate symbol. It represents this any one true behavior. In practical design, OR gates are used to combine multiple requests or conditions. For example, generating an alarm when smoke or heat is detected, or asserting an interrupt when any one of multiple sources requests service. In real digital systems, OR gates are frequently used to combine multiple requests or interrupts into a single line. For example, if any subsystem requests service, an OR gate can raise one common interrupt signal to the processor. OR gates are also used for alarm and alert triggers. If any one of several fault conditions becomes true, such as overtemperature, undervoltage, or overload, an OR gate can assert an alarm output immediately. Another important use is in control logic, especially for FSM transitions. If a state machine should move to the next state when either condition A or condition B happens, OR logic is the natural way to implement that decision. More generally, OR represents any either-or decision logic. The output becomes true if at least one input is true. Now observe the waveform example at the bottom. Inputs A and B change over time, and the output is Y equals A plus B. Notice that the output goes high whenever A is 1 or B is 1. Even if only one input is high, the output remains high. The output becomes low only during intervals when both A and B are 0 at the same time. So the waveform reinforces the OR rule clearly. The output is high if any input is high, and low only when all inputs are low. Now, let's delve into the fascinating world of the NAND gate, one of the most crucial gates in the realm of digital electronics. A NAND gate is quite simply an AND gate followed by a NOT gate, meaning it produces the inverted AND output. The NAND output becomes 0 or low only when all inputs are 1. For every other input combination, the output remains 1 or high. For a two-input NAND gate, the Boolean expression is written as y equals NOT of A dot B, which is y equals A dot B. Now, confirm this using the truth table. When A and B are 0 and 0, the AND result is 0, so NAND becomes 1. When the inputs are 0 and 1, AND is still 0, therefore NAND remains 1. When the inputs are 1 and 0, AND is 0, hence NAND is again 1. Only when A is 1 and B is 1, the AND result becomes 1. And after inversion, the NAND output becomes 0. On the right side, notice the NAND symbol. It looks like an AND gate, but with a small bubble at the output. That bubble indicates inversion, which is why NAND flips the AND result. A key reason NAND is so important is that it is a universal gate. That means we can build NOT, AND, OR, and any complex digital logic function using only NAND gates. So the takeaway is NAND outputs low only for the all ones case, and it is widely used as a fundamental building block in digital IC design. Now, let's look at the common uses of the NAND gate, and then verify its behavior using the waveform. First, NAND is called a universal gate. This is extremely important in digital design because it means we can build any combinational logic function, including NOT, AND, OR, XOR, and complex expressions, using only NAND gates. That's why NAND gates are heavily used in CMOS logic and standard cell libraries. Second, NAND gates are commonly used to implement inverters and AND/OR logic, using NAND-only networks. Designers often use NAND structures to optimize area, speed, and power depending on the technology. Third, NAND gates appear everywhere, in control logic, decoders, and multiplexing structures, where we combine multiple conditions and generate qualified outputs. Now, observe the waveform at the bottom. The top two traces represent inputs A and B, while the bottom trace depicts the output, y equals AB prime, which corresponds to the NAND function. Notice the key behavior. The NAND output remains high for the majority of input combinations. The output dips low only during the time intervals when both A and B are high simultaneously. That is precisely why the slide highlights the condition, only when A equals 1 and B equals 1. So the waveform clearly reinforces the NAND rule. If either input is 0, then the output is 1. Only when both inputs are 1, the output becomes 0. Now let's discuss the NOR gate. A NOR gate is an OR gate followed by a NOT gate, meaning it produces the inverted OR output. The NOR output becomes 1 or high only when all inputs are 0. If any input is 1, the output becomes 0 or low. For a two-input NOR gate, the Boolean expression is written as y equals a plus b, which means not of a or b. Now verify this using the truth table. When a and b are 0 and 0, the OR result is 0. And after inversion, the NOR output becomes 1. When inputs are 0 and 1, OR is 1, so NOR becomes 0. When inputs are 1 and 0, OR is 1, so NOR is again 0. And when both are 1, OR is 1, so the NOR output stays 0. On the right side, notice the NOR symbol. It looks like an OR gate, but with a small bubble at the output. That bubble indicates inversion, which is why NOR flips the OR result. Like NAND, NOR is also a universal gate, which means any digital logic function can be constructed using only NOR gates. Now let's look at the common uses of the NOR gate and verify its behavior with the waveform. First, the NOR gate is a universal gate, just like NAND. This means we can construct any digital logic function, not, or, and more complex logic, using only NOR gates. This is useful in standard cell design and also in logic optimization. Second, NOR is often used in control logic where the requirement is that none of the conditions should be true. In other words, the output should become high only when all the monitored conditions are low. This is common in fault-free checks, idle detection, and certain safety conditions. Third, NOR gates help us create not, or, and functions using only NOR networks by applying De Morgan's theorems. This is a common technique when implementing logic in a NOR-dominant style. Now observe the waveform at the bottom. Inputs A and B are shown on the top two traces, and the output is y equals negative a plus b, which is the NOR function. Notice the key behavior. The NOR output becomes high only during the time intervals when both A and B are low at the same time. That is the all zeros condition. As soon as either A becomes 1 or B becomes 1, the output immediately drops to low. So the waveform confirms the NOR rule clearly. Output is 1 only when A equals 0 and B equals 0. Output is 0 when any input is 1. Next, let's understand the XNOR gate, also called the XNOR gate. An XNOR gate outputs 1 or high when the two inputs are the same. That means if both inputs are 0, the output is 1, and if both inputs are 1, the output is also 1. If the inputs are different, one is 0 and the other is 1, then the XNOR output becomes 0 or low. So the easiest way to remember XNOR is, it is a match detector or an equality gate. Now, look at the Boolean expression. XNOR is the inverse of XOR. So we can write it as y equals AX prime is equal to. Another equivalent form is y equals AB plus A prime. This form clearly shows why the output becomes 1 in the two matching cases, both 1s or both 0s. Now, verify this using the truth table. When A and B are 0 and 0, XOR is 0, so XNOR becomes 1. When A and B are 0 and 1, XOR is 1, so XNOR becomes 0. When A and B are 1 and 0, XOR is 1, so XNOR is 0. And when A and B are 1 and 1, XOR is 0, so XNOR becomes 1 again. On the right side, notice the symbol? It looks like an XOR gate, but with a small inversion bubble at the output. This bubble indicates the NOT operation, which converts XOR into XNOR. Now let's focus on the common uses of the XNOR gate, and then understand its timing behavior through the waveform. The most important use of XNOR is as an equality comparator. Since XNOR outputs high when two inputs match, it is perfect for checking whether two bits are the same. In multi-bit comparators, we use XNOR gates on each bit pair and then combine the results to decide whether two binary numbers are equal. XNOR is also used in checksum and parity-related logic, especially for match checking, where we compare received data against expected patterns or reference values. Another practical application is digital locking or key match logic. Here, XNOR gates compare an entered code with a stored code. Only if all bits match does the circuit generate a valid unlock signal. At last, XNOR finds its application in pattern matching, especially within control logic, where certain combinations indeed must align perfectly with expected values to activate a control action. Now behold the waveform example at the bottom. Inputs A and B evolve over time, and the output is expressed as y equals A plus B. This indicates the essence of XNOR. Notice the key rule in the waveform. The XNOR output goes high when A and B are equal. That happens in two cases: A equals 0 and B equals 0, and A equals 1 and B equals 1. The waveform labels these as match 0, 0 and match 1, 1. Whenever A and B are different, like 0, 1 or 1, 0, the output drops low. So the waveform reinforces the main takeaway. XNOR is a match detector, high for equal inputs, low for unequal inputs. Now let's see. How do we realize a Boolean function in SOP form using a two-level and/or implementation? In this example, the function is f equals AB plus AC. This is a classic SOP expression because it is a sum of product terms. Step 1 is to generate the complemented variable. We need A prime, so we pass A through a NOT gate to obtain A bar. Next, we build the first product term using an AND gate. AND1 takes A prime and B, so the output of AND1 becomes P1 equals A prime B. We build the second product term. AND2 takes A and C, producing P2 equals AC. Finally, we combine the two product terms using an OR gate. So, the OR gate output is F equals P1 plus P2, which matches our original expression. Now, look at the circuit diagram. The NOT gate creates A prime. The top AND gate generates A prime B. The bottom AND gate generates AC. And the OR gate sums them to produce the final output Y. So the key idea is SOP realization means AND gates for product terms, followed by an OR gate to sum them, giving a clean two-level implementation. Now let's see how to realize a Boolean function in POS form using a two-level OR AND implementation. In this example, the function is written in POS as f equals A plus B, A prime plus C. This is called a product of sums because we are multiplying, meaning ANDing, two sum terms. Step 1 is to generate the complemented variable A prime. So we pass A through a NOT gate to produce A bar. Next, we build the first sum term using an OR gate. OR1 takes inputs A and B, so S1 equals A plus B. Then, we build the second sum term. OR2 takes inputs A prime and C, so S2 equals A prime plus C. Finally, we multiply the two sum terms using an AND gate, so the output becomes F equals S1 S2, which matches our original POS expression. Now, look at the circuit diagram. The NOT gate creates A prime. OR1 generates the first bracket term, A plus B. OR2 generates the second bracket term, A prime plus C. And the final AND gate multiplies both terms to produce the output Y. So the key takeaway is, POS realization means OR gates first to form sum terms, followed by an AND gate to multiply them, giving a clean two-level OR AND structure. Now let's implement the same SOP function using a NAND OR realization. We begin with the SOP expression F equals AB plus AC. The main idea here is that we will build the inverter and the product terms using only NAND gates. Then we will use a final OR gate to sum the product terms. First, we generate A prime using a NAND gate configured as an inverter. That is done by tying both inputs of the NAND to A. A prime equals NAND A, A. So the first NAND block produces the complemented signal A bar. Next, we build the first product path for A prime. We apply A prime and B into a NAND gate, which produces A prime B. because this is the inverted product. We pass it through another NAND used as an inverter again by tying inputs together to get back the true product, A prime B. Similarly, for the second product term AC, we apply A and C into a NAND gate to produce AC. Then we invert that output using another NAND inverter to obtain AC. At this stage, we have both product terms available, A prime and AC. Finally, we use the OR gate to sum them. F equals A prime B plus AC. So, this diagram shows a practical method. NAND gates create inversion and product terms. Extra NAND inverters recover the true products, and the final OR gate combines the terms. Now let's understand a NAND NOR realization, where we use NAND gates to generate intermediate terms and a NOR gate at the output to complete the function. In this example, the circuit begins by forming two NAND outputs. From inputs A and B, the first NAND gate produces AB prime. From inputs C and D, the second NAND gate produces CD prime. So at this stage, we have two inverted product terms, AB prime and CD prime. Next, these two signals are combined using a NOR gate. Remember, a NOR gate gives the complement of OR, so it produces AB plus CD prime. This stage is important because it applies De Morgan's theorem, allowing us to transform the structure into a POS-style realization using complemented terms. Finally, the last stage is another NOR-based inversion at the output to generate the required final expression shown on the slide. Y equals A plus B plus C prime plus D prime equals A prime plus B prime D prime equals A prime plus D prime.